Hi everybody. In this snapshot video, I'm going to walk you through some of the very basic counting principles, walk you through several problems illustrating how you count. Now I do things quite different than most books, so you're going to see a different routine, but to me it kind of illustrates the things you look for in a counting problem, the things you have to take into consideration, and when you need to take it into consideration. But first, I'm going to summarize some of the things you're going to run across in just about any book you may read. The foundation to any counting problem is the fundamental counting principle. And basically what this is saying is that when you choose an item from several different groups, for example, suppose I have a group of teachers, and I have another group of students, and I have a third group maybe of parents. And when I am choosing items from each one of these groups, okay, and the selection from one group has nothing to do with the selection from another, meaning this concept of independence, that is what we're referring to here, then the number of ways we can choose an item from each group is going to be the product of how many ways I can choose from each individual group. So in other words, if I had 5 teachers here and 8 students here and 10 parents here, and I needed to pick a teacher, a student, and a parent, then I'd have 5 ways of doing it from the teachers, 8 ways from the students, and 10 ways from the parents. And again, assuming this concept of independence, that is, the way I picked a teacher had nothing to do with picking how I picked a student or a parent, then the fundamental counting principle says the number of ways I can do this is just the product of these 3 numbers here. That's what we mean by the fundamental counting principle. It can be generalized into what we're going to be seeing later on in terms of permutations and combinations, but that's the basis of counting, the fundamental counting principle. So for example, suppose we have 3 people applying for an accounting job, 5 people applying for a secretary job, 4 different people applying for a technician job, and we want to know how many ways the 3 positions could be filled. Alright, so once again, we're identifying, or what we need to do here is we're going to have to pick an accountant. We're going to need to pick a secretary. We're going to need to pick a technician. Now, the accountant obviously has to come from the 3 people applying for the accounting position. The secretary is going to have to come from the 5 people applying for the secretary job. And the 4 people that are applying for the technician position will be what we get to choose for in terms of picking the technician. Anyway, well, if we go to pick the accounting, there's 3 ways to do it. Secretary, 5 ways. Technician, 4 ways. Again, on the assumption that picking one from any particular group has nothing to do with the other group. For example, suppose Alice is going for the accounting position and Tom was applying for the technician position. Okay, if Alice and Tom we knew couldn't work together, then picking one might exclude picking the other. Then we would no longer have this independence. But since we have independence, the fundamental counting principle applies, and the answer to this problem is just 3 times 5 times 4. The next thing we look at is the concept of a permutation. A permutation is when we're selecting from the same group several items. And the order in which we select them makes a difference here. So if I had a group of, say, students and they were forming a committee, okay, and I had to pick a president and a secretary and maybe an accountant from this group, when I choose somebody would make a difference, because if I picked you first, you would be president. If I pick you second, you would be secretary. So this is an example of a permutation. I'm choosing from the same group 3 items, but when they get selected makes a difference. That is what we refer to as a permutation. There is formulas that you will run across, and here's an example of the formula. I actually will not be working with the formula. I'm going to be doing things a little bit differently. I'll explain that in a minute. Sort of just summarizing things for right now, okay? Things that you should have run across in your reading. So, again, this was an example of a permutation. Now, here's an example. Another example. Say, these things are unedited, so you get what you got, okay? All right, just let me know if I ever do something wrong and I don't catch myself. All right, we have a group of 8 students in an art contest. 4 students are going to be selected for first, second, third, and fourth prize. And we want to know how many ways we can do this. Well, if you think about it, I'm going to have to pick somebody to be first. I'm going to have to pick somebody to be second, another person third, and then fourth. And when I pick them, they're going to come from the same group, the group of 8 students. Okay? Now, I'm going to select somebody. I'm selecting somebody, and so the order in which I select you makes a difference, because if I pick you first, you get first place. If I pick you second, you get second place. So this is an example of a permutation. So I'm going to kind of walk you through it since I have it here. When I go to pick first place, there are 8 people in the box. So there are 8 choices. Now the thing is, I can't put you back to be picked again, because that's something that's going to come up later on. Sometimes things can be put back. Well, if I'm going to have first, second, third, and fourth place, okay, and we're assuming nobody can win all the prizes, that should be a problem actually here, but assume nobody can win all the prizes, because usually when you say first, second, third, if you're first, you can't be second, right? Right? You just can't be. In a race, you come across the finish line, you're first. You don't back up and then you're second, right? So you can't put them back. So once I pick somebody, there's no longer 8 people, so I go to pick the second place, there's going to be 7. Likewise, there's going to be 6 for third. And then I only have 5 choices come fourth. And there you go. 8 times 7 times 6 times 5 is going to be the answer here. I am not going to do the math. I'm going to assume that you can take care of it. This is just the way I'm labeling it. So there's your answer. 8 times 7 times 6 times 5, whatever that comes out to be, would be the answer to this problem. Then another concept that is discussed related to permutations is that of a combination. For a combination, we're going to be choosing from the same group, not replacing things, but we really don't care what order we choose the person or thing in. So for example, suppose again we're selecting from students, okay? But the only thing is, now that it's just going to be, you're on a committee. You're a person on a committee. You're a person on a committee. So we're not going to have a president, secretary, and accountant. We're going to pick 3 students that are on a committee. Well, when I pick you, it makes no difference, because if I pick you first, you're on the committee. If I pick you third, you're on the committee. I didn't say anything different here. Up here, when I picked you first, I said you were president. But if I picked you third, you were accountant. There's a difference when you got picked. Permutation. Here, doesn't matter when you get picked. Combination. Once again, if you looked in the book, there are several formulas that can be applied. Here's an example, one of them. But again, when I get into my counting routine, which I'm going to explain shortly, we're going to see how I work the problems. All right. So in a way, I'm actually going to kind of get started right now. All right. So in this example, we have the 8 student finalists in an art contest, similar to above here. Now, instead of having a first, second, third, and fourth prize, we're just choosing 4 students that are going to go to the state finals. How many ways can this be done? Well, what I'm going to do is I need to pick a student to go to the finals. So, students final 1. Another student to go to the finals. A third student to go to the finals. And a 4th student to the finals, right? From there, I got to pick these students from the 8 students. When I go to pick the first student, I have 8 choices. Again, I can't put this student back. Why? Because I need to pick 4 students to go. If I put them back, I could pick the same person again. So once again, if I can't put things back, notice the numbers are going to start going down. Because every time I pick something, there's one less in the box. Now, I have 8 times 7 times 6 times 5. Now, if you think about this, especially later on, what I'm actually doing here is a permutation. If you think about up here, when you do a permutation, this is what's going on here. A permutation, you care about the order. Now, without getting into details here, this is how you handle this. Since this is a combination, I don't care when somebody got picked. If you were first, you went to the finals. If you got picked fourth, you went to the finals. No matter when you got picked, you were labeled the same. You're going to the finals. Well, I picked 4 things. I don't really care about the order in which I picked them. Well, again, if you read over the book, this is kind of a summary. I'm trying to get through this rather quickly, so there's a reason for this. But in order to get the overcounting, I overcounted here because, again, I was considering order. I really don't care when they got picked. I selected 4 things. The way you can order 4 things is 4 factorial, or 4 times 3 times 2 times 1. So I have to divide out by this number. That's actually what this formula is telling you. Okay? You count down how many you're going to select, but then if you don't care about the order, you have to divide out by a factorial, meaning you count down from the number you actually selected. I selected 4, so it's 4, 3, 2, 1. Right. So now I'm going to walk you through some general problems here. And first off, I'm going to kind of tell you the order in which I do things when I am trying to count. Okay? Let me put it on pause for 1 second. Okay, this is my routine on how you count. The first thing you do is I list what you need to do. Okay, maybe I need to pick a teacher, a second teacher, maybe a student, another student. Maybe I need to pick one parent. So the first thing I do is I make a list. I label what I am doing. Maybe I'm picking a president, vice president, secretary, whatever. Second thing I do is I ask where are they coming from? That's a coming from, okay? Yeah, we'll erase it. Coming from, right? That is, I say the teachers are coming from the teachers. Maybe there are, for example, 7 teachers. The students are coming maybe from 8 students, and the parent I'm selecting is coming from maybe 100 parents. Wherever they're coming from. So the second question, where they're coming from, I like to draw little boxes to indicate where I'm selecting from. Step 3, I start to pick. Or I start counting. This is when I start counting. This is where I'm going to ask the question, can I put something back? This is the concept of replacement. When I choose something, can I put them back? It's somewhere in the problem, you'll find that piece of information. But this is when I'm concerned about it. So, for example, I'll just go up here. I picked the first teacher. There are 7 choices. I may or may not be able to put the teacher back. For example, maybe I'm assigning a teacher the role of collecting papers and a teacher is grading papers. It's possible the same teacher could collect the papers and grade the papers, right? If that were the scenario, then I could possibly put the teacher back and my second choice would be a 7. But if I were talking about sending 2 teachers on a field trip, then I can't put the teacher back because I need 2 teachers there. So in my third step, when I actually start counting, I start asking, can I put them back? And this here is based upon individual groups. Meaning, sometimes one group you can put back, but maybe the students, I can't put them back. Okay? So you can have, remember, you have to make this decision on a group-by-group basis. That's why I like to draw my little boxes to make sure I'm identifying where they're coming from. So, again, either I'm going to be going from 7 to 6, if I can't put them back. Students, maybe 8, then 7, and then 100 for the parents. But again, if I could put maybe the student back, then that would stay at 8. But anyway, that is step 3. You start counting. You ask the question, can something be put back? Now, let's kind of assume that up here, this is what we have right now, okay? Maybe we couldn't put people back, all right? So right now, that's what our product is. If we might be done, we may not. But we have a 4th question. And the 4th question, does it make a difference when something is selected? Meaning, order. That's the next question. Do we have order? Something like, do we have a permutation? When you get picked, it makes a difference. Or is it a combination? Does it not matter when you get picked? In our bubbling little example here, if all we're talking about is going on, like, for example, a field trip, we're taking 2 teachers on a field trip, 2 students on a field trip, 1 parent on a field trip, we would not care about order. And when we have order, if there is order, we're going to be dividing. We will be dividing by the number selected factorial. Not the number we get to choose from, but we select from the number selected factorial. And this, again, is based upon the individual groups that we're choosing from. For example, the teachers might be organized. They might have a president and a vice president. There would be order there. The students may not be organized. They just might be going on a field trip. So there'd be no order. Likewise for the parents. Well, if we don't have order, suppose we're just choosing 2 teachers for a field trip, 2 students for a field trip, 1 parent for a field trip, then we would not care about the order of the teacher. We would not care about the order of the students. And, well, we would not care about the order of the parent. We're only picking 1. But the denominators are factorials, actually, of how many we selected. So if there were 3 teachers going on a field trip, this would be 3, 2, 1, not 2 times 1. If there were 5 parents going on a field trip and we didn't care about order, we would have 100, 99, 98, 97, 96 divided by 5, 4, 3, 2, 1. Do the math, you'd have the answer. So here are the 4 steps in my counting process. List what we need to do. Where are they coming from? Start counting. Does it make a difference when something's selected? Order. Okay? And well, step 3, we asked the question about, can something be picked twice? All right, so I'm going to end this video here. What you can do next is I'm going to have the second video, part 2, which is actually we're going to walk through the problems. But this is the way I am going to count. It is usually quite different than what you will read in most books, okay?